It's an even greater pleasure to be here. So thank you very much for the invitation. Yeah, the title looked a bit shorter when it was on the website and a bit long inside a million font. So the title of the talk is a growth fragmentation found in the cone excursions of Brownian motion and the quantum disk. It's very possible that of the four concepts here, Brownian motion is the only one that makes sense to you so far. If that's the case, and that's okay, I will sort of go through all these things as they appear. And I warn you up front that the brackets around the quantum disk are there because it's like one slide in here, but it's important for the motivation. So this talk is joint work with William De Silva, who is in the University of Vienna, and Ellen Powell, who's in the University of Durham, who I think will be here next week. Okay, so let me start then by explaining this idea of cone excursions. So we're dealing with a planar Brownian motion, so Brownian motion R2, and there are going to be two types of cone excursions that are going to be important. So the first one, and these are not so standard terminologies, I've kind of invented them for the talk, but the first one I call the boundary to apex cone excursion. So here you have some Brownian path, it's doing its thing, at some point it enters the set, it stays inside the set for some positive amount of time, and it exits at the apex of this cone with the apex angle theta. Of course, if you just put down a cone in the plane, this is never going to happen with probability 1. But if you allow the apex that you exit at to be random and to depend on the Brownian path, then this can occur as long as theta is bigger than pi by 4. So these things can happen in a Brownian motion. This is called boundary to apex excursion. And the other type that I'm going to need is what I call a whole path excursion, whole path cone excursion. And here you have again this cone with apex angle theta. And this time, all of the path of your Brownian motion from time 0 until it hits the apex is contained inside the cone. So here, you're allowed to enter it from one side and exit. And here, the entire path is contained inside this cone. And again, same deal here, that the actual positioning of the cone is random and depends on the path of the Brownian motion. Okay. So what I want to do next is I want to focus on these boundary to apex cone excursions. And I want to kind of decompose the Brownian path into these excursions, or into these bits where it stays inside a cone. And I can't do anything as simple as saying, okay, well, I look for the first time it happens, and the second time it happens, and the third time, and so on, because obviously Brownian motion doesn't look like what's on the screen. It's super wiggly. You get tiny, tiny cone excursions that happen sort of all the time in some sense. And so the way to deal with that is to say, okay, let me look at the times when I'm not in an excursion like this, or when I'm not in any cone at all. And I call these cone-free times. So these are colored in red on the picture here. So you can show, I'm not going to go into more detail on this, but you can show that that set of cone-free times is regenerative in the Mason-Nerve sense, which allows you to, first of all, cut out these cone excursions, and then define what is called what is called, I suppose, an inverse local time. So you can find a functional that increases just on those cone-free times, and its inverse is going to be a stochastic process whose range is, the colors do not appear super great on this board, which is a shame because there's a lot of color in the talk, but the range of this inverse local time is exactly these red path sections, the cone-free times, and it kind of skips over all of the excursions. So if you follow the Brownian motion at this inverse local time, then you follow the red bit, you reach what would be an excursion into the cone, and you just jump over it and move straight there. This is the Brownian motion, what we call Brownian motion subordinated by this inverse local time. So it moves along those, skips all those excursions. You can do the same thing with these whole path excursions, but I'm going to try to avoid getting into that in this talk. We do need it for the work, but it felt to me when I was writing the talk like it kind of got in the way of the rest of it. I'm going to try to avoid that. Any questions about the cone excursions? Is this sort of object, does the object make sense? Okay. Right, So now this is what I want to do. I take a Brownian motion, or any path sort of derived from a Brownian motion, and I'm going to fix a particular time t. And on the picture is marked the Brownian motion at that time. And what I do, and I'll describe how to do this precisely in a second, but for the moment what I do is I go through, I start over here, right, the path starts here and ends over here. I go through and I find boundary to apex cone excursions as I encounter them, and I cut them out. So there's that bit of path goes away. And then I try to remove as much of the other side of the path as I can while still being inside, while still making this into a whole plane excursion. So if I look here, right, I want all of this bit to be in some cone. This is going to be the cone. If I remove all of this path afterwards, everything that's left stays inside that cone for the whole of time. So I can cut all of this out. I could potentially cut out less, right? I could cut it here instead, for example. But I'm trying to make the smallest sort of path contained in a cone that I can. Do that. Do the same thing here. Found another boundary to apex excursion, cut that out. Can I shorten my path? Not really, so I leave that side of it as it is. Find another boundary to apex excursion. This one starts at this side of the boundary and goes there. Cut that one out and everything up to it. Shorten the path on the other side again. And so at every step along this procedure, I've got a cone excursion, a cone path, I don't know if excursion is the right word really, containing the targeted point, the BT. So this we call the excursion targeting the time t. But let me give a slightly more rigorous definition of this now, using this inverse local time so that we've got something sort of precise to talk about. So same deal, and I'm just giving exactly the same picture but with a bit more notation on it. So I take my time t, I look at my Brownian path up until that time, right? So I sort of pretend that this bit isn't here and define my inverse local time on that bit of the path. So the range of this tau t is all of the cone-free times up to t. And the reason I'm doing that is I don't want to cut out t. Right? So t might be contained in a cone excursion, but I want to keep t. Because I'm trying to focus in on t with this idea. Okay. So I take my inverse local time tau t. I run it up to some, let's say, some level a, right? That might be, this point here is at the end of that excursion is where I end up by doing that. I do the same thing, so I cut that out. I find, again, the smallest time that makes all the rest of this path into a whole path excursion. I cut out the stuff after that. And EAT, or ETA maybe I should say, ETA is the difference between these 2 points, right? The difference between the start point and the end point. So we're thinking here that we've got a cone a cone with apex at the end of this path. And this here, this ETA, is this whole path which forms an excursion ending at that apex, which lies along the Brownian path. Okay, and now I increase A. So as I increase A, I'm going to move further along this path in this direction. So maybe next, I said that already, maybe next I cut out this excursion. I didn't change the apex. Next I cut out this whole bit up to here, and now I had to change the apex as well. And every time I'm sort of making my excursion smaller and still keeping t in there somewhere. So I'm saying it's targeting t, it's sort of zooming in on t. And you can imagine that as A gets bigger and bigger, eventually you're just going to end up with t and nothing else left. Okay. So this is going to be the sort of object that I'm interested in. And now, that's targeting a single time. What if I want to target 2 times? So here's one of these excursions that targets t. But what if I'm interested in another t prime? So here's bt prime. You probably can't see this in the gray in this projector. Here's t prime. Okay, so t prime isn't included in this excursion because it got cut out. It was in one of these other things that I cut earlier on. So obviously, this is not the right excursion if I want to target t prime. Instead, if I wanted to target t prime, I might end up with something like this. And now the t got cut out instead. And so you can think perhaps that as you sort of go along with your targeting and cut out more and more pieces, actually every piece that you cut out obviously contains some other times. And so every piece that you cut out, which is another cone excursion, actually contains some other times that you might want to target as well. So as you go along and you're cutting stuff out, you're constantly like making a choice, which side of this thing do I go to? Do I go towards t? Do I go towards t prime? Or t double prime, or t third, or t fourth, or whatever. And so what comes out of this, if you think about targeting all of the times, which in principle you can do, because this is sort of an almost sure operation here that I'm sort of defining. In principle, you can do all of this for all times simultaneously. You just have like an uncountably big thing that you're looking at. There's some kind of branching happening, some kind of branching process, branching structure in here. Because as you go along, you have to make these choices about which place you're going to target, and that's like the system sort of branching into two, one targeting t, one targeting t prime. Follow along the one targeting t. Okay, now I have to make a choice. Do I target t or t double prime? Okay, that splits into two, splits into two, splits into two. So I want to somehow describe this branching that happens in a sensible way, in the way that where I can really say something sort of rigorous about this. Right. So I'm going to do a few things in order to do this. I'm going to try and make the object that I look at simple as possible, because so far we've had this kind of excursion valued process in some sense, which is a bit difficult to think about. I'm going to do two things. So first of all, I'm going to swap the cone for the positive quadrant. So I'm just going to map the cone to the positive quadrant. I can do that. That's a linear map. The Brownian motion, if it was standard on the left, becomes correlated on the right. And the correlation coefficient just depends on the angle theta. And now when I look at all these excursions that are going along, centered at different points, I just want to focus in on the initial displacement of this thing. So you have this whole excursion, it starts somewhere, ends somewhere. The initial displacement is the starting point, because the end point is 0, because I've centered it like that. Right? And then even more than that, and here's an important restriction, but even more than that, I'm going to look at just its L1 norm, so just the sum of the components of that initial displacement. And here I'm making an important, very big restriction that I'm just going to focus from now on, pretty much through to the end of the talk, I'm just going to focus on one particular apex angle, which is 2 pi by 3. This is basically the angle that makes this last step work, that makes it a sensible thing to do to summarize this two-dimensional thing with its L1 norm. So to go from that 2 to 1-dimensional thing. All right. And on the slide is a sort of sketch of the way that L1 norm, which I've called ZTA, evolves as A increases. So there's basically two things that can happen. Okay, it can wiggle about a bit continuously, maybe. You might think that anyway, as you sort of move through the cone-free times here and move through times here. But it can also move by jumps. And that's because as I move through my cone-free times, I cut out these blue excursions. So this pretzel excursion gets cut out. That maybe corresponds to this jump down here. That's one way in which I can move by jumps. The other way I can move by jumps is by cutting stuff out at the end of the path. And that would be this red excursion getting cut out. That would be these red jumps down. So these are the two ways in which my Z moves, in which my Z decreases, as I make my excursion smaller and smaller and smaller and smaller, as I gradually focus in on the special time t that I've picked. And eventually, this isn't totally obvious maybe, but eventually this thing does just come down and hit 0. So from now on, this theta equals 2 pi by 3 is going to be in effect. Everything that involves this L1 norm has to be in that special case. We could talk more about why at the end, maybe. Good, okay. Right. So I've talked about cone excursions, and now I've hinted at some kind of branching process involved, and now I'm going to give a description of what that process is. This is just going to be an intuitive level. I'm not going to give a rigorous definition of growth fragmentation because, I mean, I only have 18 slides. I would need like 45 to actually write down definitions of everything. So a growth fragmentation for us is going to be a system of particles, which in our world, these are the excursions that target all these different times, right? So the different times basically are the different paths through this particle system. Each of those particles is summarized by a particular trait, which in our case, this is this L1 norm of the initial displacement that we looked at in the previous slide. And if I look at one of those particles and just follow it on its own, so just look at the marginal law of the evolution of that trait for that one particular particle, that should be a Markov process. So if you look at this one, for example, this was ZTA, right? So this thing is going to be a Markov process in its marginal law with only downward jumps. That's okay. Those downward jumps are cutting out of other excursions. And where every jump is accompanied by the birth of another particle, which is independent of its parent and of the other child, conditional on the initial value of the trait. So here, for example, I've got this path, initial particle going along. Here it jumps down. And remember that that jump down was because I cut out a bit of a cone excursion. But that cone excursion actually contains a bunch of other times. So it should get its own particle that lives on and does more branching and more cutting out and all of this stuff. So this is the picture. And we finally, on only slide 8 out of 18, we're able to state a result. So before I say the result, I should say, so far I've always talked about, okay, I've got some Brownian path, some B. Right? I'm going to focus particularly on the case where I start out with one of these boundary to apex excursions, and the boundary point, like the initial point, is fixed. So I start at some Z on the boundary, and I hit the apex at some future time. So with that, the theorem, in the sort of vague version of it, is as follows, that these particles, in other words, the times that I'm targeting, with traits ZTA, this is the L1 norm summary of these excursions I'm cutting, or I'm finding. These particles T with traits ZTA form a growth fragmentation whose law we can characterize. And this picture, the theorem more or less says that the picture on the right corresponds to the picture on the left. Basically, that the things I've told you so far are true. Okay. So this is a vague version. I'm going to say a bit more about what the law of this thing looks like, so how we can characterize it. But before I do that, I want to give you 2 additional bits of information. So first of all is this relationship with this quantum disk, which I promised there will be a slide about. And secondly, some of the connection with the literature, because there's quite a lot of it out there, looking at similar models. All right. So first of all, the relationship with the quantum disk. Okay, this is like very, very, very whistle-stop tour of this sort of area. I don't pretend to be an expert in this part, so this is more for motivation. But this is where the problem came from, right? So otherwise, without this slide, I think it looks like we're just playing games with Brownian motion, which is fun. And I would do that anyway, right? But there is some additional motivation. So a quantum disk is the ball of radius 1 in the complex plane, where you give it a Riemannian metric, which is e to the gamma hz times the standard Euclidean metric, and the h is a Gaussian free field. This is, you have to make sense in terms of some kind of like normalization procedure, because on its own this doesn't really make sense because h is not a proper function. But by now this is sort of classical, and then this gives rise to some disk with some kind of Riemannian metric on it, random Riemannian metric. Okay. This is not working anymore. Oh, yes, it is. Now I take gamma equals √8/3. That corresponds to picking theta equals 2 pi by 3 in our cones picture. And I mark a single point on the boundary of this disk, minus I. Now I do even more stuff. So I draw what is called a counterclockwise space-filling SLE6 curve, started at this point. You can think of this as a random curve drawn on this disk, which fills all of space and eventually ends up, so it goes off in this direction counterclockwise, and eventually ends up back at minus I, having filled everything in. The interesting thing is that this curve has branches. So as it goes around and fills space, you can see here, for example, that it sort of cuts out bits of the disk as it goes around. And we call these sort of bubbles that it fills out. And those bubbles are the ones that are not containing the target point of the particular branch, and they get filled in by a different branch. And our growth fragmentation process describes the total, so the sum of the left and right boundary lengths of the different branches targeting different points. And the boundary length is measured in this Riemannian metric that was given at the top. And when I say it describes this, I don't just mean like it has the same law as this. I mean there is like a one-to-one sort of correspondence between these branches and their left and right boundary length and the cone excursions that we found and their L1 norm. Okay. So this is the one slide about the quantum disk. Okay, so a bit of prior art. So these boundary to apex cone excursions that I described on the first slide were explored by Duplantier, Miller, and Sheffield in 2021. This is the Mating of Trees paper. They did it in reverse time, so they were starting at the apex and going to the boundary, and we'll come back to that in a minute. The whole path cone excursions were described a lot longer ago by Legal in 1987, and we use that as well in this work. And now we come on to different sort of growth fragmentations that have been seen before. So one of these was done by Elie Aidekon and William de Silva, which was kind of the same model that we have, but with theta equals pi. So that means you have kind of half-planar excursions, so excursions away from a line, if you like, in Brownian motion. That's quite interesting, and our work sort of builds on this in many ways. The relationship that I described on the previous slide with the quantum disk comes from this Mating of Trees Duplantier, Miller, Sheffield paper. That was for, I guess, like a whole plane version, and Ang and Gwyn paper studies the disk in particular. So another growth fragmentation very much connected with the one that I'm describing here was found in what is called the conformal percolation interface of the CLE conformal loop ensemble carpet. This was a paper of Miller, Sheffield, and Werner. And so kind of what's going on here is that I'm going to butcher this probably, but you kind of have these CLE curves. So you take your quantum disk, you draw CLE curves on it, which kind of form sort of almost like obstacles for an SLE curve that moves through them. That's this conformal percolation interface. And you describe then, this paper describes the left and right boundary length of that object. And in some sense, what we're doing, so their parameter regime was for gamma bigger than √8/3, and our work is kind of getting to the boundary of that. And sort of what happens is the CLE carpet thing vanishes, and you get left with just the SLE. This is a bit vague, but I think this is what's going on. And two more other sort of connected growth fragmentations, one of them in the Brownian disk using the snake construction by Legal and Riera, and one in random planar maps by Bertoine, Budd, Kurian, and Korczemski. These two are very much connected with what we're doing, but these two objects here, the Brownian disk and random planar maps, describe random metric spaces. And the growth fragmentation that arises here is from looking at the points in the metric space that are a certain distance from the boundary of the space, which is not quite the same as what we're doing or what Miller, Sheffield, and Werner did as well. But the type of object that appears is the same. Right. So in the roughly second half of the talk, I want to go into a bit more detail about this growth fragmentation that I've sort of conjured from nothing. And in particular, I want to say a little bit about what we can say about its law and some like particular bits of this branching system. Okay. So when I described this process, I was targeting individual times. And I said, okay, actually, I want to target a fixed time, and then I want to target another time t prime, and then eventually like all the times. But what's actually very nice is that you can also target a random time. So you have your excursion starting from the boundary, hitting the apex. It has some lifetime. If I pick a uniform time in that, in between 0 and that lifetime, I can also target that. And I can look at the excursion that targets that time. So this would be Z capital T A, as A increases. If I do this, I get some path that starts at, I don't know what, 1, say, and goes down and eventually hits 0, going down by jumps. When it hits 0, that's the end, that's the lifetime of that particular piece of the growth fragmentation. And I can time reverse it from there. So then I'm going to get something that starts at 0 and goes up by jumps and eventually hits 1. So here's a theorem that is telling me something about the growth fragmentation, which is that the S that I get like this, the time reversal of ZT, has the distribution of a 3/2 stable process conditioned to stay positive. And moreover, I claim that this characterizes the growth fragmentation as a whole, the full system of things. Okay. Maybe it's believable, and I won't spend too much time on it, that this does characterize everything. Because if you think about what we're doing here, if I want to characterize the distribution of this whole branching system, well, I've got branches towards all these different points, and what I have here is a branch towards a random point, but that random point could be any of the other ones, right? So there's sort of a positive probability, or I suppose a positive like probability density, that this random time is actually a particular fixed time t, or lies inside a certain time interval. So by understanding what happens as I go towards a random time, I get information about all of the times simultaneously. And this idea has a long history in branching processes. It goes under different names, kind of a spine decomposition, a many-to-one lemma or description. So perhaps it's believable that we really can, just by looking at this one random branch in the system, describe the whole thing, at least describe the distribution of the whole thing. So I'm going to set that aside, and I'm just going to look at this 3/2 stable process condition to stay positive, which arises here. And okay, this is a really nice part of the work, I think, and I would have been quite happy with this on its own. It kind of leapt out at us, and I think this is a really nice thing that we sort of found by chance in some way. So a beautiful construction of the 3/2 stable process condition to stay positive. Right. I'll describe this from the start. So, okay, everything here is in reverse time, first of all, right? So before I was taking my path and kind of cutting bits out, and here I'm going to be starting at a single point and building an excursion from that single point going outwards. So this is all reverse time. Okay, so take this point. This could be 0, right? I don't care where it is. I draw 2 Brownian motions. W prime goes in the forwards time direction. W goes in the backwards time direction. So W prime is going right and W is going left here. Of course, in reality, they'd get all mixed up straight away, but it helps keep things straight. This gives me a process X, which is indexed by time in the real line. Now, I have this inverse local time still, and now it's for excursions that start at the apex of cones, which are now quadrants. So start at the apex of quadrants and go to the boundary of quadrants, so like this blue one here. And I'm going to look at x at one of those inverse local times. So one of those, you can think of it as like the endpoint of one of these excursions. And now I try to build a cone excursion that contains that bit of the path. So let sigma be the first time for this backwards Brownian motion that the quadrant then with apex at x at w of sigma, or x of minus sigma, contains the entire path from that time up to x of tau a. Hopefully you can see this is like the backwards version of what we were doing on like slide 2 or whatever. But by doing this, we can build it out forever. So before we had to start with a path and cut bits out. And if we start from the single point and build it outwards instead, we can go as long as we like, right? We just make A bigger and bigger. Because the W prime goes on forever. And so does the W. Right? So I take these two marked points with the hollow disks, and the difference between them is what I call YA. So we can think of this as being like the initial displacement of a cone that is centered here, a cone excursion that is centered here, sorry. And curly S of A is going to be the L1 norm of this YA. And this curly S is the thing that I claim has the distribution that I want. So the theorem that will imply the previous one is that this curly S is a 3/2 stable process with positive jumps and conditioned to stay positive. I'm going to try to justify this theorem because I think this is quite interesting. This is a construction of a conditioned Markov process, a pathwise construction of a conditioned Markov process. Usually when you want to build a conditioned process, you do it with some kind of singular conditioning operation, or you do a Doob-H transform, or you do something clever like that. And here there's no change of measure involved here at all, right? I'm taking a 2D thing, I'm doing some weird operation involving cones, and I'm ending up with this S, which is a 1D 3/2 stable process conditioned to stay positive. That's kind of weird and cool. Okay, so actually, before I go to here, let's think about what this thing does. Okay, so here I'm building an excursion out and sending it to the right and to the left in the picture anyway. How does this excursion grow? Well, it can grow in two ways. It can grow on the right by discovering a new blue excursion, starting at the apex, going to the boundary. If I do that, then my y will go either jump to the right or it will jump upwards, because going from the apex to the boundary in the quadrant means going right or going up, because it skips over those blue things. I can also extend this path by going off to the left here, by discovering one of these new red pieces of path. These are actually cone excursions in the Legal sense, but I'm trying to avoid that as far as I can because the talk's long enough. If I do that, then what happens is the apex of the cone gets displaced down and left at the same time. And what that means is for y, because y is the difference of the start point and the apex, that means that y jumps up and right at the same time. So what does that mean for y and for s? So on the left at the top is a sketch of how y moves, right? So we're starting at the origin there at time 0 and going forwards like that. It messes around a bit, and when it jumps up or right, the blue jumps. And if it touches the boundary of the quadrant, it can also jump up and right at the same time through one of these red jumps, through discovering something on the left. And that translates, so both of those types of jumps, of course, translate to jumps upward for S, the L1 norm. And if you just look at S on their own, they're sort of indistinguishable, right? If I don't know where they came from, if I don't have the Y picture, I've got no idea which of these jumps are red and which are blue, unless I include some extra information. Okay, so as I said, these blue jumps come from seeing these new apex to boundary excursions. These were described in the Duplantier-Miller-Sheffield paper, and those blue jumps are the jumps of a 3/2 stable process, which goes up or right. So looking at the L1 norm, it means that you just go up according to the same jumps. The red jumps come from seeing new whole path excursions. And these, this is proved by Legal, come from or are the same as the jumps of a 1/2 stable process, where the jump distribution is sort of unknown, or was unknown in Legal's work. And then you do something else that mixes them, right? So you get these red jumps, but you're also sort of mixing the red and the blue bits because of the sigma that was on the previous slide, because you have to wait until the blue, yeah, anyway. So these are sort of mixed together in a funny way. So if I want to complete this proof, I have to do three things. I have to work out what the distribution of the red jumps is. So that's sort of completing a particular aspect that was left implicit in Legal's paper. I have to show that this process S on its own is Markov, which is not at all obvious. The Y is Markov, but the S, because you don't know where your jumps are coming from, it doesn't have to be. And also, and this part is a bit technical, I suppose, but you have to show that the red jumps, if I just look at S on its own, the red jumps occur at rate 1/SA. If you have all these things, then it's, I don't know, less than a page of calculation to show that the thing you get out is really the conditioned stable process. That's all I'll say about this, but I think this is a really fun result. It echoes a bit a result of Bertoine in, I think, 1993, which did all this kind of one-dimensionally and had another pathwise construction of the conditioned stable process. There's a bit of a similar flavor, but it's definitely not the same construction, because ours goes from 2D to 1D, and his sort of went from, you push two paths together in some way. That's not true. You took one path and you did kind of a funny time change of it. So I don't think one implies the other, but it's quite interesting that there's these different ways of pathwise constructions of conditioned things. Okay, right. And then I think this is probably the last slide with like real maths on it in the talk. So I just want to give you why does this tell us anything about the growth fragmentation? Well, if I take this path that I built, sort of out of the marked point and going outwards, and I go to the end point here and time reverse it, so I'm going to call this E bar A. This is a cone excursion ending with the apex here. I can do this for any A. Like I said before, I'm not constrained in how big A is. I can just build this out as long as I like. It's completely arbitrary. So now I take A, capital A, to be random, and to have the law of Lebesgue measure. So I don't know if it's right to call this random, but it's under an infinite measure, A is distributed like that Lebesgue measure. If I look at E bar A with the random A, together with A as a pair, that has the same distribution as a generic whole path excursion. This is this Legal excursion measure that I've sort of swept under the carpet a little bit, together with a time chosen uniformly within its lifetime. And actually this is true for all theta. This is not just true for theta equals 2 pi by 3. This gives the connection with the growth fragmentation. Okay, so in summary, what we found, isolating excursions targeting a given time and cutting out excursions targeting others gives us this growth fragmentation process, and there's a strong connection with stable processes in the distribution. Along the way, we found this new construction of conditioned stable processes, which I'm not going to stop banging on about. We also found as part of this the law of the initial displacement of this whole path cone excursion, only in the case theta equals 2 pi by 3. The other thetas, this took us long enough, the other thetas are still inaccessible to us, at least to me. We also obtain, I haven't talked about this, but I'll say very briefly, the law of the so-called locally largest particle in this growth fragmentation. So you have this whole system of branching things. If you focus in at every branch point at the particle whose trait changes the least at that branch point, that's called the locally largest one. And we can find the distribution of that as well, basically using this condition stable thing that I described before. And we also find a special martingale, which this is something that you get almost for free from having a branching process. But the interesting thing is that this martingale has a limit distribution, which is the same as the lifetime of the typical excursion. And because of, I guess, some stuff that's on the next slide, this recovers some results about the volume of Boltzmann triangulations that can be proved combinatorially. Okay, so a quick look back then on the literature and our relation to it. So the growth fragmentation that we found is exactly the same one that was found in the Brownian disk by Legal-Riera and in this Boltzmann triangulation framework by Bertoine, Coréen, and Korczemski. Like I said before, what we do, the actual construction, is not the same, is not analogous, right? I think because what they are doing is, like I said, this metric exploration from the boundary, so points at a fixed distance from the boundary, and what we are doing is more like a percolation exploration of the space. But that's very heuristic, at least for me. The process we have is in the same class of growth fragmentations that were found in this percolation of CLE carpets by Miller, Sheffield, and Werner, and in the metric exploration of other random planar maps with faces with large degree by Bertoine, Coréen, and Korczemski. And these two things, of course, the two things in orange should be connected as well. Okay, I think it's totally possible that one could derive our results using some quantum gravity arguments, so some sort of Liouville quantum gravity arguments. But we don't, apart from this motivation to give the relationship with the quantum disk, we don't use anything that isn't Brownian motion. So this is a purely sort of Brownian argument that gives rise to this. And I think, so for me personally, that's interesting on its own, that we get it with this sort of, I don't know if low tech is the right word, but sort of very like fundamental techniques. I'll end with a couple of open questions. The first of these is, we have different types of excursion here from the first slide. So some start at the boundary and go to the apex, some start at the interior and go to the apex. I colored all of these jumps and stuff that I drew in all the pictures, right? But actually in the result, there's no colors, there's no types. And I think it would be very natural to try to type it, right? To try and like sort of develop a theory, well, it's partly developed already, but to try and use a theory of typed growth fragmentations and understand how that type, boundary or interior to apex, evolves as we follow particles. What about theta not equal to 2 pi by 3? I already said that theta equals pi was done by Ada, Con, and De Silva. Of course, theta not equal to 2 pi by 3 is sort of connected with the gamma not being root 8/3 in the quantum disk picture, and therefore it's connected with the CLE carpet thing and the planar maps thing. And I think probably, okay, from the perspective of these kind of quantum gravity surfaces or random metric spaces or something, those are the right objects to look at. But I do wonder whether there's something else to be done just with Brownian cone excursions there without involving additional objects. But this is wide open for me. So my secret interest in the whole thing is, are there perhaps other nice constructions of these condition stable processes? Because all the stuff that we did with this L1 norm, it's really, really specific to theta equals 2 pi by 3. So extending that out would be really interesting. I have a few thoughts about that, but nothing concrete. Final question, can we start things at 0? So we're always starting on the boundary and going to the apex. You'd think you should be able to start at the apex, so go away and come back in. Right? I think it probably wouldn't be too hard to define a Brownian path that does that. And then can you analyze the excursions within that? And that should be connected to something like the Brownian map. And I think that's it. So the paper we're still writing, actually. The maths is done. I'm hoping this will be out within the next month, maybe 2 months. So again, co-authors William De Silva and Ellen Powell. And that's all. Thank you very much. Yeah, so the stable process can be viewed in 2 ways. You can see it as a Levy process, or you can see it as a self-similar Markov process. And actually, it's the thing that lies at the intersection of those two. So yes, it is a positive self-similar Markov process. It's also a Levy process with particular Levy measure. This is what happens when you try to put 4 objects into one title. That's right, yeah. Thank you very much.